So today we are going to start the graph theory part. So in this syllabus we don't have many things about graph theory, but the things that we have we are going to start. But before that, let us try to explain the theory of graph with some examples and through some intuitive idea. So it was a long problem. I'm talking about Konigsberg Bridge Problem. So the problem is stated like that. Suppose we have a river. So this is a river. So I can color it down here. Maybe we can put it here. So this is the river part, and there are two islands. Okay, so they are the islands. C and D are the islands, and A and B are banks. So the riverside portion. Okay. So basically, you can say that there are four lands A, B, C, D, and this is the river. So here also there is another branch of river, and due to this branching, this island it formed. Two islands are formed. Okay. So this the whole idea is you have some bridges. So this is bridge one, say bridge one, bridge two, bridge three, bridge four, bridge five. Say we call it say bridge one. Say I call it E1. Maybe in red I can write it. Say this is bridge one. This is bridge two. Say this is bridge three. Say this is bridge four, bridge five, bridge six, bridge seven. So there are seven bridges so that you can come across from this side to this side and so on. Now the idea is, suppose you start from a place say A, and you have to travel all the bridges exactly once, and you have to come back to the position A once again. That means you may start with say like this. You start with this, goes through here, then you have to travel to this, you have to go to all the bridges, you have to travel all the bridges exactly once. So you can come back here and you can travel to this, and suppose if you go here, you came to A, but you have not exhausted yet the E6, E5 and E7. So again you have to go here. So this way you can come this way, but now you are stuck because there is no bridge left for you to travel through E5. So this is one way that I travel through this one, then this one, and this one, and then this one, and then this one. So I had many other options to take. So the question is, you start from some place, maybe from A, you have to travel all the bridges, and you have to position A. The only condition is, if you travel through one bridge you cannot travel. That means if you go through this, that means this bridge is closed for you. If you travel through this bridge is closed to you. Now the question is, can you find a way so that you start from A and then go on traveling through all the bridges and come back to A once again? So that's the idea. So it was a kind of problem that was in Germany, Konigsberg. It's known as Konigsberg Bridge Problem. Now the idea is, can you find such way? So all of you should try with this. Can you find such way, some path? Maybe you can describe like this: A, then E1. So this is E1, so that we can all understand. This is E2, E3, E4, E5, E6, and E7. So can anybody tell me any of such options?
So it will not be possible. So
Okay,
because
so Pratik explained that it's not possible, but have you ever tried with this?
yes, sir. So there it will if we go out through one bridge, we must come through another bridge. the path to be complete.
Yes.
So the bridges must occur in pairs for any part of the land. But we
Yes.
see that D and C have odd number of bridges connected
Okay.
to them.
Okay. So I request all of you to at least try at least once and see what is the problem. So Pratik explained a nice way. It is not possible, but you should convince yourself that it's really not possible and try to find out what was the reason that why it's not possible. Okay, I am giving you few more minutes to think about yourself and try to draw this, and then it will be easier for you to think that why it's not happening. Okay, maybe for a better way of representation, that's the advantage for mathematician. Mathematicians are very imaginative. They can draw whatever they look like or they whatever they think. So instead of drawing such a original river and all, mathematician can represent the whole thing. Maybe I can just copy it there from here. Mathematician can represent the whole thing by using a very simple image by this. Yes. Okay. Now you can see that it looks like a mathematical image, and you will be surprised to know that this image, the whole messy river bank and the island image, is mathematically same as this very simple looking image. How it looks like. So just try to think about the whole island A. I can consider this as a point, a simple point. Okay. And if I have a bridge from here to say C, so all these islands or lands or banks, I consider them as points. So this is A is a point, C is again a land, that is another point, B is again a bank, that means a land, I consider it another point, and D is another island, I consider it to be another point. Okay. So ABCDs are mapped with this image, simple looking image. Now the question is how the bridges will look like. So you see that from A to C, how many ways that you can, how many bridges are there that can lead you from A to C? There are two bridges, that is E1 and E4. So here you can write it like this is E1. So this is E1. So you can think of this is E1 and maybe this is E4. So both E1 and E4, they will go help you to move from A to C. So A to C, there are two bridges, E1 and E4. Similarly, from C to B, there are two edges. There are two bridges, that is E2 and E3. So I can write it E2 and E3. From C to D, there exists exactly one bridge, that is nothing but E5. So this is E5. And from A to D, there exists exactly one bridge, that is nothing but E6. And this is E7. So now I can, the actual image can now be translated with a very simple looking mathematical image, and that is with some few arcs with few points, and that we can represent this, the whole original image can be now represented using the very simple looking image, and we call this is as a graph. So now the question is, the graph is made up of what? So you can see that there are basically two components, two major components. One components are these points, so they are the points. So there are 4 points and few arcs. These arcs may be a straight line, may be a curved arc. That means a curved line. Okay. So two components are there. the points and few arcs. We call these points as vertices. So they are called vertices, or if I singular is vertex. So a single point is called vertex, whereas this arcs, so this is one arc, this is one arc, they are called edge. So two components are important, vertex and edge. So you can understand that one edge, for example here E6 is an edge. So this E6 is basically associated with two vertices, that is A and D. Now you can think of which one you should write first. Shall it be AD or DA? So in this graph, since we are not concerned with the direction, because here there is no direction mentioned, these two notions are equivalent. That means AD and DA, both of them, they will represent E6. But if by any means we have some kind of direction, for example, when you travel through a road, sometimes you might have seen that one way. That means it's not a both way. Some places in Calcutta, you might have seen that these roads maintain a one way. For example, in front of our Presidency University, you can always see that the buses or the cars, they will always come from the side of, say, Calcutta University direction to the College Street, the 4 junction. That means it's a kind of direction. So you have a kind of direction. So if you have a kind of direction, and if you can say that A and B are two vertices, then A and B, this edge is called a directed edge. So that will certainly not be same as BA. So this, if the directions are involved in a graph, we call it directed graph. So for many practical applications, sometimes we have to impose some directions on a graph, then we call it directed graph. But many of the times we consider only graphs where no directions are mentioned. For example, here we have not mentioned any notions of direction. That is why we call it undirected graph. So this is undirected graph. Okay. So in case of undirected graph, AD and DA, they are basically the same, that represent the edge E6. Whereas in case of a directed graph, AB will not be same as BA. Okay. So what we understand, that to have a graph, we should have two components. One is set of vertices. So here usually in terms of graph theory, we represent the set of vertices as the set V. So a graph, if I consider G to be a graph, then G should have two components, V and E. So here V is the collection of all vertices. So in my above image, V is set of the 4 vertices A, B, C and D. And E is the set of collections of all edges. So here E is nothing but the collection of all edges E1, E2, E3 to E6. Okay. So what is edge? So for each edge, you can also think of edge as a kind of function which associates with two vertices, may not be distinct. Note that two vertices may not be distinct. For example, if I have this, suppose if I have a graph like this, say I have say 3 vertices A, B and C. So suppose this is my edge E1, E2 and E3. I might have another edge like this. which starts from A and which ends at A. We call this kind of things as loop. Okay. So loop means a vertex which starts from an edge which starts from an edge and which ends at the same edge, same vertex, which starts from a vertex and which ends at the same vertex. That means A to A basically. So that is a loop. Okay. So in a graph, we might have a loop. Also, there is another term. This is called parallel edge. So this is one edge. This is another edge. Okay. We called these two edges as parallel edge. Okay. So these edges are called parallel edges. So two important terms are here. One is loop, another one is parallel edges. Many of the books, they describe a graph as a simple graph. Simple graph means a graph that does not have any loop or parallel edges. That means a graph which does not have, for example, this is an example of a maybe like this, maybe I can write it, say this. So this is an example of a graph. It has many vertices. For example, all of them are vertices. If I write it like this, A, B, C, D, E, F, G, H, I, J. So there are A to J. There are many, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 vertices and there are edges. So this is E1, this is E2, this is E3, E4, E5, E6, E7, E8, E9, E10, something. So there are many edges, there are many vertices, but look at, none of these edges are loop or parallel edges. So parallel edges means you will have two of the vertices and there will be at least two edges which starts from the this vertex and ends with the same vertex. Okay. So they are called parallel edges. But if I write something like this, if I draw like this, then that will be a parallel edge. So this and this will be a parallel edge. But in this image, in this graph, there is no parallel edge. So I think all the terms now it's clear to you. Now let us have a look. Have a again we have a look at this image. So here the whole thing is basically represented by this image, right? So I can write it in a maybe like this. I can just redraw this image. So this is A, this is my C, this is my B, and this is my D. Okay. So this is a parallel edge. This is a parallel. Sorry, this is a parallel. Oh, this is another parallel edge. Okay. So the edges here are E1, E4, E3, E2, E7, E5, E6. Okay. So now the whole Konigsberg problem can be translated into this, and it was around 1700, and I forget exactly the date, maybe a year, maybe 36 around, when Euler for the first time solved this problem. So before that, many people, I mean, in that city, many people, they had a work. So they had a very good evening work or morning work, maybe. They tried to resolve this issue just by taking some arbitrary path and trying to see whether it's possible or not. But Euler, for the first time, he mathematically thought about this problem and he solved this problem in that way that Pratik explained us. That see, if you start with this, say if you start with this, and if you want to come back to here, that means if you come back to here, then there should be even number of ways, because if you are exhaust with this edge, you cannot come back through this edge. So if you are going somewhere and if you need to come back again, then you should have even number of ways to do that. And that's very interesting way. Unless you draw this, you have to just try to solve this problem, like all the people started the way that they did it. If you try to draw few of these paths, then the logic behind it will be quite clear to all of you. And that was the first mathematical understanding that Euler gave to us, and it is considered to be the first idea towards the starting point of graph theory. And from then many people started working on this, and in today's scenario graph theory plays an important role in many aspects, Okay, so now if I again give you this image and say I may not have a, let's see, I have the book with me. This maybe I have the original image here, maybe. Yeah, so this is the original image from here. So this is the book from Norsing Dio. I will follow this book. Okay, if I just put it again somewhere, and if I ask you the question, okay, so now it's clear to all of you that it's not possible to come back to A exhausting all the bridges exactly once. Now can somebody tell me that I give you a permission that you can put extra bridge between. So you can construct some extra bridge. Can you construct some extra bridge so that the problem can be solved? So here there exist 7 bridges. Now my point is, I have given you a permission to have some extra constructions. So now you can construct 3, 4, 5, 6, even 7, 8, 9, 10 bridges. So now the question should be how many minimum number of bridges that you can construct so that the problem could be solved. Can you explain? So how many minimum number of bridges can be constructed, and you have to give me the position where it has to be constructed so that the problem could be solved.
Sir, just one.
Okay, just once. Okay, just everybody should type. Can you please type it? So just tell me from where to where. A,
Sir,
B, C,
from the
D, like this.
sir the
Just type it so that I can see all of you.
sir the from the island D to
Don't tell, please don't tell. Type it. Yes, so that others should have also some chance to. Please type from where to where. Okay, Somebody already mentioned. Please, all, could you please type so that the problem could be solved? The question is clear to all of you, right? Okay, now Akash, tell me, from where to where you want to make it?
So the island D to the land A.
D to land A. Okay, so from here to this, right? So according to Akash, this should be a new bridge. This one, right? Okay, will that be sufficient? Any other solution? So this is Akash bridge. AKA you right? Akash? AKA,
Yes,
what
sir.
is your
ASH.
spell? AKSH, right? So this is Akash bridge. Okay. Any other bridge? This is the only answer.
So now the sea still has odd number of bridges. So if we enter it, we cannot go out of it. There will be
Okay.
some stage we will exhaust the bridge.
Okay. Now
Well,
Akash will tell me how to explode with this. So I will write it E1, E2, E3, say E4, E5, E6, E7, and now you have E8. Okay. Now Akash, tell me how to explore. So what would be your path? You start with A, then which bridge you will take? Akash, are you there? Akash, are you there?
Sir, Akash has left the meeting.
Oh, left the meeting. Yes. So Pratik has pointed out that still that would be a problem. So any other solution? Anybody?
so
Any?
B to D and A to C, two bridges.
Okay. So your solution is something different. Okay. Let me remove Akash bridge now. Akash bridge is being removed. Yeah. What is your plan?
So add one bridge from A to C.
A to C. Okay. Let's it be Pratik bridge. Pratik one. Yes. Another one.
So B and D.
B and D. Okay. B and D. Like this maybe. Some new design bridge. So this is Pratik bridge 2. Pratik 2. Now can you please tell me what would be your path? So this is my E1, E2, E3, E4, E5, E6, E7, and then E8 and E9. E9 is Pratik 1, Pratik 2. Okay. So this is E7, sorry, E8 and E9. E9, yes. Now, can you please tell me how to go? So start with A, then which bridge you take? Pratik, can you complete your
E1, sir.
E1? Okay. Then
So
you are in C.
B.
Okay.
Yes, A is a C. Yeah, yes.
You are in C. Then which bridge you want to take? So
So
it's already exhausted. Just a minute. It's already exhausted. Then you take E2.
yes, sir.
E2, that means this bridge is also exhausted. Then you are in B.
B.
Then
So I enter C again through B, E4.
So E4, then you are in C. So this
Yes.
bridge is exhausted. Then,
Sir, from C to D through E5.
okay, so E5, so you are now in D. So this is also exhausted. Okay, then D2,
Uh, so I think there will be a problem because E3 will not be. Uh, so I think there is a problem. I will not be able to take E3 again.
yes. So you cannot take E3, but so you are in D now, right?
Yes, sir.
Then where to go?
Like D to E7, E7 to D.
Sir,
Uh, sh-
sir,
yes. Shall I continue? Yes.
sir, E5 and again, we except not going E5, we can take from E4 to E8, then come back to E3, then take E5. Then
Just a minute. Could you please repeat? First of all, is the writing okay? Is the bridge construction places are okay? You are not
yes, sir.
modifying the construction,
No,
right?
no, no. I'm not
Okay.
modifying the construction.
Okay. So what
I
you are doing is you are defining another path. So A to E is E1 is fine. This is
sir,
fine. This is
before
fine.
E5, it's fine.
Okay. Up to this is fine.
Up to C, it is fine.
Okay.
From from there, we can take
Yes.
E8,
From C you take E.
E8, then come through E3.
Okay. So you take instead of E5 you take E8. That means Pratik 1, right?
Yes.
So you take Pratik 1. So this is E8 and come to A.
Come to A, then come through E3.
Okay, come through E3. So that means your this block is, so this is still alive.
Hmm. This is
So E3, that means this is also gone. That means you are still in C. Okay.
C. Then
Yes.
take E5,
Then take E5. That means now it's gone. Then
E7,
E7.
then E9,
So okay, just a minute. Before that it was in D. Then E7 means you are in B. Then you take E9.
E9,
That means this is also gone. Now you are in D.
then
And then
E6,
E6. So
then we can come to A.
A. So you have exhausted all the bridges and you come back to the position A once again. As a result, the problem that we had is basically solved. Now the question is, can we, so you had to make two constructions, two bridges, Pratik 1 and Pratik 2 were the two constructions, new constructions, you made it. But Akash tried to do it with only one construction and somehow we found that that may not be feasible. So the question is how many the minimum number of bridges? Is the two optimal or even you can make it with one? So that's a question that one can ask. Okay, so if I write this new bridges or new constructions and if I redraw the whole thing, then how it should look like. So here we had again say A, it was my B, it was my C, and it was my D. The path was A to E, it was, can you just tell me this one E1, and I had E3. Now I had again another, right? This is E8 and C to B. Oh, sorry, it should be C. Just it should be A to C and it should be B and it should be D. Now it's fine. So C to B was E4 as well as E2. B to D, B to, so here I had C to this, and A to D I had one bridge. This is E6 and this is E5, and B2 that was E7. So that was my whole idea. Now, how many bridges that you have extra constructed? E8 is the new bridge, and another bridge you have already constructed, that is from E9, right? So where is E9? So E9 is from B to D, B to D, E9. So sorry, yes, I think this is E8, not E8. This is, I think, E6. Okay, E6. Okay, now this image looks like this. So how many extra edges? So this and this E9 are the two extra edges that you have to draw so that the whole mission can be completed uh, legitimately. Okay, now you can travel from A and you can go through like this, and you can exhaust all the bridges exactly once, and at the end of the day you will again be able to come back to A. So that's the power of graph theory. So the quite complex things can be now drawn very easily on a simple pen and paper, and that can be drawn very simply. And instead of really constructing the bridge, you can check here whether that is really possible or not. And Euler finally came up with a very nice theorem that I will do it maybe after 2 or 3 classes. That's known as Euler's theorem based on graph theory, and that results actually gives us a way. It's a if and only if condition, which gives us really whether this kind of traveling is really possible to exhaust all the paths and starting from a point and come back to the point by exhausting all the paths exactly once. So that's kind of traveling point is a special kind of traveling, and that has a specific name, and I will come to all those things in details with all the theoretical details, but maybe after 2 or 3 classes. But for today's class is just for to give you a kind of motivation how graph theory plays an important role. Now you can understand for all the engineering purposes, before drawing or before having a kind of actual implementation, the engineers they do have a kind of graph. So you can have might have seen the kind of planning, that planning they draw. So that is basically a kind of graph theory or extended version of graph theory, through which they just try to measure whether it's really feasible or not. Sometimes you might have seen in the Broadway or the highway, there are a kind of loops. It looks like a spiral. When you go, it goes like you go like this, then suddenly you come up. So you might have seen in the highway when you actually enters into some cities, before entering into the cities you might have seen some kind of spiral kind of things, and then suddenly you can come out of the whole broad or the fast track of the way, and then you enters into the city and you find that lots of traffics are there in front of you. Okay, so why this kind of things and how many times that it actually moves? So it's actually basically just to avoid crossing. That means if you have too many things and there are other things are coming around, so there are many crossings. So that's why to avoid the crossings, there are few graph theoretic techniques which can be used so that you can avoid this kind of crossings and all. So that's why you might have seen in Kolkata also, you have might have seen that similar kind of things. Before coming out of a highway, you might have to travel kind of circular motions that you may feel when you are within a kind of vehicle. Okay, there are other applications, lot of applications of graph theory are there. There are another applications which is very useful, which is known as, say, community or utility graphs. So here, suppose I have 4 houses, say in a locality, suppose I have, say, 3 houses, H1, H2, H3, and suppose I have 3 kind of utility services. For example, water line. So in Kolkata or in India, it's not quite common to have a gas line. So we have electric line. Say this is, instead of gas line, you can see this may be a telephone line. Though nowadays the land telephone lines are not very common, but still you can think of land telephone line or maybe the cable line. That's still quite common, but it actually comes over the road, or it's now looks very messy to have this kind of cable line onto seen onto our roads. Anyway, suppose 3 lines are important: water line, and this is telephone line, and this is electric line. Okay. So the idea is you have to provide these 3 utilities to these 3 homes. So that means all the homes should have these 3 connections. That means you should have a water connection, home 1, home 2 should have the telephone line connection, and home 1 should have also the electric connection. That means if the houses, they will have this connectivity, you will have a kind of line, straight line. Okay. Straight line is not very important, you can have some arc. So this is utility to that home. Now the question is, you can understand that if water line goes to very nearby with the telephone line, and by some chance this water line or water pipe has some kind of damage, then you have to remove that, or you have to take care about the damaged part. So you have to dug in, and when you are going to dug in, or you have to upload things, then if the telephone line or the electric line are very nearby with that water line, then it might happen that your telephone line or electric line may get damaged. So there may be a problem. So what is the best way to install all these lines, so that even if you have some problem on your, say, electric line, and if you are going to dig in, then so that the telephone line should not hamper. That means if the line will cross with each other, and suppose there is a problem here, and if you are trying to say these 2 lines are gone through very nearby positions, and then something happens with this, while you are taking care of this, it might happen that the problem will also lead to the water line. So the best way, so that we should install the lines in such a way that one should not cross others. If they are in a, say, far apart or significantly far apart, then there should not be any problem. So the best way to install it, so that there should not be any kind of overlapping or crossing. Okay, let us try to have a look at another simple image. Suppose I have suppose I have this image, say this, and I draw like this. Okay, so say this is A, B, C, D, and I have 6 edges: E1, E2, E3, E4, E5, and E6. Now this is a crossing. Can you think of drawing the same connection in such a way that there should not be any crossing? Can you think or redraw the same image having the same property? Here the property is A and B is connected through E1, B and D is connected through E3, and so on. So can you redraw the whole image in such a way that there should not be any kind of crossing? Can somebody be help me in drawing this, redrawing this?
So you can join D and B by drawing the arc outside the square.
Okay, very good. So this is A, B, C, and D. So which one you take? B and D
Yes,
to
sir.
draw. Okay. So A and C remains the same, but what he says, instead of drawing it like this, I can draw like this. See, all the properties remain the same. So I am not drawing this one. I am drawing, instead of this, I am drawing this B to D to B, just drawing outside the rectangle. Then see, you can see that all the properties, they remain the same. So this is E1, E2, E3. So this is, I think, E5. This is E3 and E4, E6. So this is nothing but the redrawing of the whole thing. So if there was a chance that if I draw or if I install the lines like this, then there was a chance of overlapping. But if I install like this, if I say B to D, if I take my line or if I install the line in this way, then there will not be any kind of overlapping. So it is possible to draw in that way, so that the same representation can be drawn in a different way, so that we can avoid the crossing. So that's very important. And from here the term planar graph comes into play. Planar graph, planar graph. Okay, and if it is not at all possible, so now the question is, is it really possible to draw all the graphs in a planar form? That means no interaction will be there, no overlapping will be there. Is it really possible to do that? So let us ask this question to this graph. So we had the utility problems, and if I write like this, if I this, is it really possible? Can you please try to resolve this? So what I am asking you, you have this graph H1, H2, H3 and W1, T and E. So W is the water, T is the telephone, E is the electricity. Can you draw this graph in some different form so that all the properties will remain the same, but there should not be any kind of overlapping? Can you please try to do that? Is the question clear to all of you? Can you please try to draw, like in case of rectangle, what I did it like this. I redraw the whole thing just like this. So the problem was solved here. Now in a bigger graph, I just ask the same question. Can you solve this thing or redraw the whole thing in such a way that there should not be any overlapping? In my previous drawing, I just avoided the overlapping here, drawing bypassing this. Can you just draw something here also? Any idea or anything? It's quite interesting. Okay, let us give you some hints. Say I just try to redraw the whole thing. Okay, so here you can see that if I reduce it, it might be easier for you to see both. Yes. So here you can see that. So this is H1, H2, H3. This is my W and this is my T and this is my E. Okay. Now first let us try to draw with this. So this is my H1, H2, H3 and this is my water, telephone, electricity. So first to avoid the for the first house, I just install all the houses, I just install my water line. Okay. Then the best thing what you do, you try to install telephone line to all of them. Is it possible to install telephone line to all of them without having this? I can do, say I can use another line, maybe say blue. So I take this one to this house, this one, and to this house, this one. Now I need to draw the electric. So what can I can very easily do like this. I can do like this. So the only house 3 is left with us. Now can you draw house 3 a line without overlapping from E to H3? Can you have any line without overlapping? And if you can do that, how can you do that? And if you cannot do that, why you cannot do that? Any argument? And that leads to a very important theorem which we will describe. The proof is not within the scope of our syllabus, so we'll just state the theorem, but maybe after a few classes. But you can intuitively understand what is the difficulty here and why you cannot really draw without overlapping. What would be a problem? So you can see that the only thing you need to do is that E and H3. So you need to draw an arc between E and H3, but some intuitive idea is there which actually will stop you to draw without overlapping. So can you try to explain, or can you give me some hints?
Sir,
Yes.
if we try to connect E to H2, then we can either go through right side or left side of H3. If we
Yes.
take the then we will intersect the line from water supply. If we take the right, then the electricity from the path electricity to H3 will be intersected by telephone to H2. What I am trying to say is to connect telephone to H2, we will either intersect water line of house 3 or electric line of house 3.
Yes, that's true, but
Both
there is
sides.
a, yes, you are absolutely right. But the point is, uh, if you think it in a mathematical way, then what is exactly happening here which actually stopping you? Try to think in a math. Your perspective is exactly fine, but try to think it in a mathematical way that something is there which actually stopping you. Something is closed. Something is there. I'll extend it. Maybe it would be. Oh, it's too extended. Yes. Anybody? Any guess? So try to look at the location of this and try to think about the arcs. Suppose I have like this. Say this is one point, this is another point, and say this is another point, this is another point, and say this is another point. Okay. I need to go from here to say another point here. Can I go from here to there? Say I have to go, say not from inside, I have to go from outside like this. Can I go from here to there? I can go like this because there is some place which not yet being exhausted by this, so I can go into this. But if this is closed and I need to take an outer side of this, I might have gone through this, but suppose this path is not allowed to me. I have to take an outer route, and this is already closed. Can I go into it without intercepting this? Now you can understand, try to think this point and this point. See, this is and this is, so this is basically surrounded with all the points, which makes it a closed. So there is no way that you can get in. There is no way that you can get in without intersecting any of these lines, because they are all closed. So there is a concept, it's a inside and outside things, and due to this insideness and outsideness, if you are going to get in from outside, you have to cross some of the edges, and that's the idea. And again, that was given by Euler, and few more interesting results. The proof is there, but we are not going to, may not be able to have the see the proof here. If you are interested, you can certainly see the proofs, but we'll just go for some formulae and all, and that is sometimes very important. Okay, so is the idea clear to all of you? Is there any question? Please ask me if you have any
Sir,
question.
sir,
Yes.
how can we ensure that it will always be close to there should be no argument?
No, I mean, that's the actual theorem, but in this case, in the drawing that we have made, that you can see. So
Yes.
that's why I told you it's an intuitive idea, not the exact proof. The
Okay,
exact
sir.
proof will consist formal arguments and all, but it's a kind of demonstration. That's why I told you, in whatever way that you are trying to do, you always find that you are basically making a two regions, one
Yes, sir.
inside, one outside. And due to these two regions, from outside to inside, you have to cross the edge. That's why you cannot draw in that way. That means for this image your answer will be no. That means for this utility case you cannot draw the graph in such a way there should not be any overlapping. That means for this image there must be a kind of overlapping, and as a result we call it graph as a non-planar graph. It's not a planar graph. So this planar graph terms will certainly come into our syllabus, and we'll discuss about it in little detailed, not much. You also have in a postgraduate syllabus, we also have graph theory where you will have more results. But here we have mostly the basic idea of graph theories and few preliminary terms. But what I try to emphasize is these terms are very practical. So now you can understand that for practical purposes, graph theory plays an important role. For example, nowadays you are basically using very sleek, smart mobiles. So when, if you remember, you might be very child at that time when the Nokia mobile came into play, and you might see that this Nokia mobiles were a little bit thicker, quite heavy, but very robust. So I liked that kind of mobile, but it didn't have your touch screen or it didn't have your smart facilities that you have today. But why these mobiles are getting so thin and so weightless? For example, when you had your initial television at your home, you might have seen that the televisions had some back portion extended. Now the screens are quite smart. For example, our monitor, our laptops, they are day by day they are getting thinner and thinner. So the question is how you are making it so thin, or how you are it looks so sleek. So there graph theory plays an important role. So all the things are basically the circuits. Now there is a one research is going on that how this circuit can be fabricated so that it will take less place. That means you can draw like this. Suppose you have some of 2 points you need to join, or some say these points you need to join. So you can draw like this, or the same thing can be drawn like this, like this. So which one you should take? The smallest path you should take, but sometimes it happens that if you take always the smallest path, then some overlapping might be there. Not also only that, you might have seen that your mobiles are sometimes getting hotter, because if some more process are going on, or if you are talking with somebody for so long, then you may find that some of your mobile sets, they get hotter and hotter, because it sometimes due to this, if you are very close with some circuits, sometimes one interferes with others, and as a result it might happen that some heat may generate. So the same research will continue, that how to optimize this path. That means, so that you should have some kind of tolerable amount of heat should be generated. At the same time, the path length. For example, if you are fabricating something from this place to this place, the less number of, or the less path that it should travel, it must have some function with the cost. If it has some less amount of place, if it takes, then it might have some space efficiency, but at the same time it might interfere some others. For example, you may not have very good connectivity, your signal problem may be there or something. So both way, you cannot reduce everything in a very small place, because something may interfere some others. That's why lot of researches are going on how to optimize this, how to interfere this, how to minimize the interference and all. And there the graph theory, especially for hardware fabrication, graph theory plays the most important role there. So it's not only for while making our roads we use graph theory just to reduce the number of crossings and all. While we have the fabrication in hardware, we do graph theory. So there are plenty of places where we have lots of applications of graph theory. Okay, so let us again
Sir,
have some, yes,
sir, the previous problem, sir, if we take any one, if we take any one point and join the other 3 points with that point, and we then if we proceed with the second point, then after we have joined the second point with the other 3 points, we always uh, have a quadrilateral,
yes,
which forms a boundary.
yes. So you cannot say quadrilateral because it's may not be a straight line. Yes, it's a
Yes,
bounded region. So you'll
I, I
always
can
end
I
up with
can
a bounded region. Yes,
I can take the point and redraw the graph in such a way that I can form the quadrilateral.
yes, that's fine. But in a
So
graph theoretic way, we don't say it
yes,
is a
sir, yes.
quadrilateral, but it's a closed region. That's important.
Then I can say that if we have this type of configurations, that means this utility graphs. So if we have 6 vertices or more, then we can
Yes,
always we can never do this, because
yes,
always we have at least 3 on the other side,
yes,
and 2 on the other side. So this problem will again happen.
yes, exactly. So with three vertices, so when we'll go for planar graphs, you will find that this kind of graphs play an important role. So there are two another graph. So this is known as K33. So you can see there are 3 points here, there are 3 points here. This is known as K33, and there is another graph, it's called K5, complete graph with 5 vertices. So we'll come into it, and you are actually in a right track of proving this. So now the question is, how will you prove in a general form? And there the idea is basically you are basically generating a kind of closed boundary, so that to join 2 points, one lies inside the boundary, another lies outside the boundary. So you cannot have a path which will, without crossing, you can do that. So that's the idea. Yes, exactly, you are right. Okay, so now we are into graph theory, so we'll solve any many other problems as well. But so now you have some in your mind what is graph. So graph is basically consist of a vertex set and edge set. Now you know what is a vertex set, what is an edge set. So suppose this is a graph. So this is a graph, and say I have this. So I have vertices say V1, V2, V3, V4 and V5, and say edge sets are E1, E2, E3, E4, E5. Okay. So few important terms are related to this. For example, degree of a vertex. So this is a vertex. See here I have not mentioned anything about direction. So this is an undirected graph. Undirected graph. Okay. So for this undirected graph, what do we mean by degree of a vertex? So any idea what would be the degree of this vertex? What would
4.
be the degree of a vertex? Okay, so somebody says it's 4. So we call it degree of say V3 is 4. Now you can understand why this is 4, because there are exactly 4 edges which are incident on this vertex. That means which are incident on this vertex. So that's why the degree of this vertex is 4. So there are 4 edges. Who are these edges? The edges are E1, E5, E3 and E2. So they are the 4 edges which are incident to this vertex V3. That's why the degree is 4. Can you tell me what is the degree of V4? The degree of V4 is
2.
2. So the degree of V2,
1.
degree of V2 is
So 1.
1. Okay, so now this concept I think is clear. What do you mean by a degree of a vertex? So everything formally is written on the book. I am just giving you the intuitive idea so that when you are going to read on the book, you will get all the formal definition, how they are defined in exactly the same way, but it's much easier to explain you by drawing the images. So this is called degree. Okay, and this is called the incidence vertices. Now if I ask you, so if I write like this, so degree of all the vertices you can calculate. Now can you draw a graph like this, degree? Okay, so if some vertex is like this, so with this graph one vertex is like this on which no vertices is incidence, then we call it isolated vertex. So within this graph I have another vertex which is not connected with any of the vertices, that means no edge is incident on it, so we call it isolated vertices. Isolated vertice. Okay, so this vertex is called isolated vertex. So what would be the degree of this? So this is V5, so this is V6. What is the degree of V6? Degree of V6 is how much? What is the degree of
0.
V6? Is 0. Okay. Now it may happen that there is one edge, that means there is one loop here. Okay. Now if I ask you the question, what is the degree of V5 with this loop? Degree of V5 with this loop. Can you tell me what is the degree of V5 with this loop? So the question is how much it will contribute. A loop
4.
should, yes, so degree is 4. That means this loop actually contributes degree 2 to this vertex. So initially it had 2 edges incident on it, now a loop. Loop means each loop should contribute 2 to the degree of this vertex. So initially it was 2, due to this loop it is now extra 2, that means altogether 4. Is it clear to all of you now? Okay. Now if I ask you, can you draw a graph with 3 vertices, the degree of each vertex is 0. Can you draw such graph? So you need to draw a graph with 3 vertices such that the degree of each vertex is 0. Can you draw this graph? Is it possible to draw this graph?
So three isolated vertex.
Exactly. So if you draw 3 isolated vertices, then you are done basically. So this one, this one, this one. So this is my V1, V2, V3. So that's it. So this is a graph on which the degree of each vertex is 0. Now can you draw a graph with 3 vertices? The degree of each vertex is 2. Can you draw a graph such that degree of each vertex is 2?
A triangle.
So a triangle. So V1, V2, V3. Okay. Now in a graph, if some vertex is isolated, then we call this graph as not a connected graph. So this is a disconnected graph. For example, if I have triangle along with, say, this is V4, then the whole graph becomes disconnected due to this vertex. But since this graph is all the vertices are connected, that means from one vertex you can always go to another vertex by some traveling some edge, then we call it a connected graph. But if it happens that there exists some vertex to which you cannot move from any of the other vertices, then we call it a disconnected graph. Okay. So this is initially the triangle was connected, but due to addition of this V4, this graph becomes disconnected. Okay. Now let us try to draw another graph. Draw a graph G with 3 vertices V1, V2, V3 such that degree of V1 equal to 1, degree of V2 equal to 3, degree of V3 equal to 2. Can you draw such a graph? Degree of V1 is 1, degree of V3 is 3, V2 is 3, degree of V3 is 2. Can you draw some graph?
So we can join V1 and V2 with one edge, and between V2 and V3 there are parallel edges, two parallel edges.
Okay, just a minute. So V1 and V2, one edge, then
V2 and V3 there are two parallel edges.
like this. Yeah. So degree of V1 is 1, degree of V3 is 3, V2 is 3 and degree of V3 is 2. So you can do this. Now if I just modify this as instead of 2, if I put it 3, can you draw this?
No, sir. So this
Okay.
will not be possible.
Okay, let's what others will do. Let's see. Try to solve this problem. So V1 degree 1, V2 degree 3, V3 degree 3. Can you do that? Let's try.
Sir,
Okay, in a similar way.
sir,
So
V2
yeah,
and V3. I want to join V2 and V3 by 3 parallelly.
okay, let's see V1,
V2 and
V2, V3. Yes, tell me once again.
V2 and V3 by 3 parallel.
Yes, very good. Then what's about V1, V2?
By 1.
By 1. But then
Um,
the degree will be
4,
4.
4, 4, sir. It will not be possible.
So unless you draw it, you cannot have the intuition behind it. So why it's not possible? See here, if I have 3 parallel lines, up to this there was no problem. So it degree becomes 3 and degree becomes 4, 3. But when we have to consider V1, that means there must be some edge, and the edge will have some at the end is V1, but what would be the other end? It has to be either V1 or V2 or V3. But if it be other end as V2, then the degree will be 4 and not 3. And if I have the other point as V3, then the degree becomes 4. So it's really a problem. So now tell me, what is really exactly the problem? Can you identify the problem? What is exactly the problem? Why it's happening?
The total degree sum is odd.
Total degree sum is odd. Okay, good. So we are now going for a formal proof of an interesting theorem. It says that now you have all the idea of degree, incidence and all. Now the theorem says that let G be a finite graph. So finite graph means graph having finite number of vertices and edges with n vertices. Let V1, V2, Vn. Okay, E uh, let n vertices be the let this be the n vertices. Let G has E edges. So there are E many edges. Then the theorem says that the degree of all these vertices, if I take the sum, that should be twice the number of edges. Just have a look at this image. So what is that statement? Let's try to draw a peculiar looking image, say this one, and maybe this might have some parallel edges, might have some isolated vertex. Okay, so how many vertices are here? So here we have V1, V2, V3, V4, V5 and V6. And how many edges are there? 1, 2, 3, 4, 5, 6, 7. So there altogether 7 edges. So here my E is 7 and number of vertices n is also 6. Yeah, n is 6. Now let us try to have a degree sum. Okay, so sum of degree of this vertices Vi. So let's start with V1. This value is 1. What is the degree of V2? That is also 1. What is the degree of V3? Can anybody tell me what is the degree of V3? Degree of
6.
V3? 6. plus degree of V4 is 3, degree of V5 is also 3, and degree of V6 is 0. Let us try to sum up. So this is 8, 11, 14, and this is nothing but 2 into number of edges E. So that is the statement of this theorem. Is the statement clear to all of you? So if you have e many edges on the graph and there are n many vertices, if you take the sum of degree of all the vertices, then that sum should be twice the number of edges, what this says. So here the sum is actually 14 and 7 is the number of edges. So that's the point. Is that idea clear to all of you? Is the statement clear? Okay. So if it is clear, now let us try to prove this result. So the question is, how do I prove this? Any guess? It's very simple argument. So take any vertex V, okay, and take any edge incident on this vertex V. Take any vertex V and take any edge incident on it. So if it is an isolated vertex, then there would not be any edge, right? So take any vertex. What are the three cases may appear? Either there exists no edge on it, there might be one edge or some simple edge. That means V is a vertex and there must be another vertex, say V1, which is other than V. Or it may happen that there is a loop. Okay. Now three cases may happen. Either V is a isolated vertex, or there is some edge which is incident on V, but the other end of that edge is something different, V1. Or it may happen that there is some loop on it. Okay. Now if this is an isolated vertex, then there is no edge, so the sum, in this sum, the contribution of this vertex is how much? 0, because here I have put given 0 due to this V6. This is isolated. Now if there is one vertex and there is another vertex which is different from V and there is an edge between these two, then for this edge, how much is the contribution? Here the degree 1 contribution and here the degree 1 contribution. That means within this sum, for V, for this edge E, the contribution will be 1 and here the contribution will be 2. That means for each edge, the contribution is exactly 2 to this summation. So each edge, in this case, it is actually contributing 1 for this vertex and contributing 1 to this other vertex. That means it actually contributing 2 as a whole when we consider it as a E into this summation. And what happens if it is a loop? Then also for this vertex is actually contributing 2. That means if you have a edge, any edge E is actually contributing 2 to this sum of these vertices. Each edge is contributing 2 to the sum of these vertices. So if there are E many edges, so what would be the summation? Summation will be twice E. Is the idea clear? Okay, let me explain once again through this image. That will be easier maybe. So suppose I have this vertex and say I have a loop here. Let's little simpler. So V1, V2, V3, V4, E1, E2, E3 and this E4. Now we consider first E1. Okay. So and then I will check with E1 what are the vertices are involved. So with E1, V1 is involved, V2 is involved. So for this E1 to this V1, how much is the contribution? Contribution is 1 because the degree is 1 here for this E1. For V2, for this E1, the contribution is exactly 1. Okay. So as a whole, when I am summing up all the degrees, so summing up all the degrees, so degree is for V1, for this E1, the degree is 1, for E3, the degree is 1. So for V1 is basically 2, right? But it comes for two different edges. But for a single edge, for this vertex V1, in the summation of degree of Vi, the contribution is exactly 1 for this case. For this vertex, for this vertex, the summation, this contribution is exactly 1, okay, to this summation. Now for E2, who are the vertices are there? So vertex V2 and V3 are there. So contribution is 1, contribution is 1. For E3, who are the vertices? V1 and V3. Contribution is 1, contribution is 1. What's about V4? The vertex is V3, only one vertex, but the contribution here is 2. And what is for V4? There is no contribution because there is no edge. So altogether I have 1 plus 1 plus 1 plus 1 plus 2. Okay. So there are 6. So if I have this summation of degrees, then that is 6. But it came due to this, sorry, how many? 1, so how many degree? 2, 4, 6, 8. Sorry, there is another one. So this is 8. And how many edges are there? 4 edges are there. 4 edges. So that is 2 into E, number of edges. Is it clear to all of you? So either it will contribute 1, or it will contribute 2, or it will contribute 0 to one edge, will contribute either 0 or 1 or 2 depending whether it's a loop or it's a isolated vertex or it's a normal edge. Depending on that, the sum is having the formula. Is it clear to all of you? Is there any doubt or question? Okay. So now I will go to another interesting lemma. Suppose I want to have a graph whose degree should be say 1, 2, 1 and say again 1. Okay. So the number of odd degree vertices is odd here. See, can I have a graph whose vertex degree is like this? Can you draw this graph? You can see 1, say V1, V2, V3 and V4. Say maybe this V2 degree, say this is V1, V2, V3. But when I'm going to draw another graph, another vertex V4, its degree has to be 2. Can I draw this? Can I draw a graph like this?
No, sir.
Why not?
Degree sum is odd here.
So degree sum is odd here. So if I have, okay, if I like this, is it really possible? So degree is 4, V1 degree is, sorry, its degree is 0. So it has to be connected with something like this. So V1, V2 is done, V1 and V2 degree is done, this degree is done. But if I have to make V3 degree to be 1, it has to be connected with something. And when you are making it connected with something, the degree will automatically increase. So as a lemma of the previous theorem, you can say that the number of odd degree vertices must be, what should be the answer? Must be
Even.
even. So the number of odd degree vertices in a graph must be even. So you cannot have a graph with odd number of odd degree vertices. What will happen if you have odd number of odd degree vertices? If you just add them up, the number becomes odd. And if you have, so what will happen? The degree of each vertex will be either even or odd, right? So if you have taken all the even degree vertices, if you make a sum of that, you will always get an even number. If you have odd number of odd degree vertices, if you sum them up, then what will happen? You will get odd number. So if you make an even plus odd, you will get ultimately an odd. So sum of degree of all the vertices will ultimately be odd, which is not possible because it should be 2 into the number of edges, which is an even number. So you'll get a contradiction. That's why you cannot have a graph whose degree, the number of odd degree vertices is odd. So it has to be even. Is the result clear to all of you? Okay, so that's good. So that's the end of my presentation or my class today. So here, please have a look at the book by Narsingh Deo. So the title of this book is this one, Graph Theory with Applications to Engineering and Computer Science, and this is by Narsingh Deo. So I will follow this book. And in my today's class, I have done not much. I have done basically the introduction part of it. And please have a look at the chapter 1 till till this finite and infinite graphs incident. So I have done till this part. Okay, so up to this. So this is basically let's see. Okay. So please have a look before basic a brief history of graph theory. So up to page 10 of this chapter. So please have a look at this, and you can also study the in basic history of this graph theory. That is also sometimes interesting. So basically the chapter 1, the first chapter, first part of that chapter. But as a homework, what I am giving you is basically uh, solve these 12 problems. So as a homework, it's the 12 problems of this chapter. Okay. So the first chapter with these 12 problems are the homeworks. Clear? Good. So they are very simple. It's not very difficult. If you study this, it will be very easy for you to solve this. Okay. So that's the end. Any question?